In the previous chapter, the first chapter which we did, what did we discuss? We discussed what is matter. We discussed how we came to know about matter. What did scientists they said about matter? What are significant figures? And there were many other things related to matter. Now when experimentation was done, it was seen that matter consisted of certain particles. Because we know that matter, it has weight and occupies volume. Therefore, it is supposed to consist of certain particles. What is matter formed of? There were many experiments which were done regarding this. And in this chapter, the second chapter, structure of atom, we are going to do about the particles which consists of matter, right? From which matter is made up of. So when we are going to do this, let's go on to little history of this chapter. Now when we are doing this chapter, in the beginning there was one Rishi in India whose name was Maharishi Karnad, right? What did he say? He said that if we keep dividing matter, matter was known as Padarth. That when we keep dividing matter, we get very, very small particles, and these smallest particles which cannot be cut, they were known as what? They were named as Pramanu. Okay, then there were other scientists which started working on Pramanu, and the second one was Democritus, and his helper was Leucippus. Democritus and Leucippus, who suggested that if we keep on dividing matter, ultimately matter will come to that part, or it will attain a smallest particle which cannot be cut further. And this smallest particle, that was known as what? It was known as atom. Then after that, John Dalton, he did experimentation to say for the first time, he explained an atom, and he defined atom as the smallest particle which participates in a chemical reaction. So, atom, for the first time, Dalton said that he defined atom, and he also gave us atomic theory, saying that it is the smallest particle which participates in a chemical reaction. Okay? Then after that, Faraday was the first scientist. Faraday was the first scientist who said that matter consisted of certain charged particles. Faraday said that matter consisted of certain charged particles. How did he come to know about this? When a glass rod was rubbed against silk, it occupied certain charge. So therefore he said कि जो matter है, it consisted of charged particles. After Faraday's this statement, there was another scientist, J.J. Thomson, who did experimentation to verify the fact what Faraday said, that matter consisted of charged particles. So the foundation of modern picture of atom. Foundation of modern picture of atom that was put forward for the first time by J.J. Thomson. To understand that how did we come to know that matter consists of certain charged particles, or atom consisted of certain charged particles, there was an experiment which was done, which was known as the cathode-ray experiment. Positrons, it consists of pi mesons, then it consisted of electrons, and then it consisted of protons. But when we are talking of the fundamental particles of any atom, there are three fundamental particles: electron, proton, and neutron. The other ones, as I mentioned, the positron or the neutrino or the meson, they all are known as subatomic particles. Okay? Then we come to the very important cathode ray experiment. The cathode ray experiment, which was conducted to discover the electron. Okay, so the cathode ray consisted of a sealed tube, a sealed glass tube. This experiment that was started by Julius Pucker. Scientist who started this experiment was Julius Pucker, and later on there were other scientists who helped them. For example, Crook was there, J.J. Thomson were there. They also conducted the same experiment, thereby formulating the discovery of electron. Okay, so this tube, which is the sealed tube, this is also known as the Crook tube. It consists of an opening over here, which is connected to the vacuum, and it consisted of two electrodes, metal electrodes. The negatively charged was known as the cathode, and the positively charged was known as the anode. In this, there was certain gas which was taken to study the nature of atoms of the gas, and the gas which was taken initially was hydrogen. Okay, so it was seen that at normal pressure means if we are taking a pressure of 1 atmosphere, nothing was observed in the tube, which meant that at 1 atmosphere the gas was not of conducting nature. It did not conduct electricity. Okay, then after that the gas was evacuated from this side, because this opening was attached to the vacuum. So it was evacuated and the pressure was reduced to 10 raised to power minus 2. Okay, at 10 raised to power minus 2, it was seen that a faint greenish yellow rays were traveling from the cathode to the anode. Okay, and then when the pressure was further reduced at 10 raised to power minus 4, when the discharge tube had a pressure of 10 raised to power minus 4, it was observed that the color of the gas that diminished. Okay, so there were certain these 10 raised to power minus 4, there were certain these invisible rays which were still transferring from the cathode to the anode. Depending upon this, other experimentation was done so as to see the characteristics of these rays which were traveling from the cathode, right? So let's understand, or let's see what was studied? Characteristics of cathode rays. The first characteristic was that cathode rays travel in a straight line. Cathode rays travel in a straight line. How did this statement was formulated? It was seen that whenever any object that was placed in the path of these rays, a shadow was casted behind. Okay, so a shadow can only be casted if any rays they are traveling in a straight line. If they are deflected, then no shadow will be casted. Okay? So this showed that they travel in a straight line. The second characteristic was that they possessed kinetic energy or mechanical effects. They possessed kinetic energy or mechanical effects. Now, it was what was done to prove this was that there was a spinning wheel which was placed in the path of the cathode rays, and this, when cathode rays they started traveling and they hit the spinning wheel started rotating. Okay, so therefore it was said that they have kinetic energy. Now, when anything hits something, it will only move if it has particle nature. Okay, for example, if we are talking of windmills you know na, from which electricity is being conducted. So windmills also, they move only when dust particles are hitting it. Right? In a vacuum, if we place a windmill, it is not going to move. So therefore we say that they possess kinetic energy or mechanical effects, as a result of which it was put forward that these particles or these cathode rays, they had certain mass particles, matter particles or mass particles. Then third, when these rays were subjected to electrical field, when an electrical field was placed over here, let's say perpendicular to the tube, it was seen that the cathode rays, and this is the positive terminal and this is the negative terminal, it was seen that the cathode rays, they were deflected towards the positive terminal of the electric field. So when they are subjected to electric field, they get deflected to the positive terminal of the electric field, thereby proving that the cathode rays consisted of negative charge. Okay. So this was one of, you can say, a very important achievement which was seen for cathode rays. So cathode rays, they said they were negatively charged. Also they consisted of certain mass particles. So therefore it was suggested that the cathode rays, they were stream of certain negatively charged particles, and these negatively charged particles, they were termed as negatrons by J.J. Thomson. Negatrons by J.J. Thomson. Right? So these negatrons were later termed as electrons by Stoney. Stoney was the scientist who named them electrons. Okay, then another important effect, another important characteristics of cathode rays was that the cathode rays had heating effects. foil was placed in the passage of the cathode rays, that got heated up. Why this was happening? This was happening because the stream of electrons, they have kinetic energy, as a result of which when they are moving there is certain friction which they are going to cause when they hit the foil, and thus the foil that gets heated. Right? And also another characteristic is that cathode rays produce X-rays. Cathode rays produce X-rays, and also they affect the photographic plate. They affect the photographic plate. Okay, so these were certain characteristics. There's another very important thing which was seen, that the cathode rays, they were, when we are talking of the cathode rays, so nature of cathode rays was independent. We are saying that nature of cathode rays, number one, they are independent of the gas which is taken in the Crookes tube. They are independent of the gas which is taken in the discharge tube, which means that cathode rays of every matter consisted of similar kind of particles, right? And it was also independent of the nature of the cathode taken. Whatever the cathode was taken, the characteristics of the cathode rays, they were similar, there was no change. So this also suggested that cathode rays, they consisted of certain similar kind of particles which should have the same characteristics. Then obviously when we are talking of cathode rays and we are saying that they are particles, any particle should have mass, and Faraday already suggested that the particles, they should have charge. So the next you can say step towards discovery was to calculate the charge and mass of the cathode rays, or as already put forward by Stoney, these cathode rays consisted of material particles which were known as electrons. So let's find out the charge and mass on the electron. Charge and mass on the electron. Now, when charge and mass on the electron was discovered, what did J.J. Thomson do before separately talking of the charge and mass? He discovered, or he formulated the charge to mass ratio. Charge to mass ratio through his experiment. What did he do in his experiment? Now, as you can see over here in the figure, what was he doing in the experiment was, he took two metal discs, right? One is a smaller metal disc and the one is a larger metal disc, okay? So the smaller metal disc over here, this is known as the cathode, and the larger metal disc, that is known as the anode, right? Now a source of beam that was traveling from the cathode towards the anode, this source of beam which was traveling, or the beam which was traveling, that was simultaneously subjected to the electric and the magnetic field. It is simultaneously subjected to the electric and the magnetic field, and there was a photographic plate or a zinc sulfide plate which was taken as a screen. Right? Now when we are talking of electric and magnetic fields, what did he do was, he either only the electric field was working or only the magnetic field was working. Now initially when the beam of light was traveling, it was seen by J.J. Thomson that only the electric field was subjected and the magnetic field was not subjected. Okay, so when only the electric field was subjected, the cathode rays being negatively charged, they were deflected towards A, that is the positive terminal of the electric field. Okay, and when only magnetic field was applied, it was seen that the deflection was towards the other point, which is C. Now it was very important for J.J. Thomson to apply both the fields simultaneously. The fields were applied in such a manner that both electric and magnetic fields, they were perpendicular to each other, and they were also perpendicular to the propagation of the beam, to the direction of the beam, right? So he balanced both the electric and the magnetic fields. When he balanced both the electric and the magnetic fields, there was no deflection observed and the beam, it passed straight to C. Okay, so we have now, if only electric field is subjected, it goes to point A. If only magnetic field is subjected, it goes to point B. And if both are subjected but both balance each other, then there is no deflection. Right? Now, how much deflection was occurring? It depended upon the following factors. How much deflection was occurring? It depended upon the following factors. The first was magnitude of the negative charge. Magnitude of the negative charge, right? It was seen that greater the magnitude of the charge, greater was the deflection, right? So more the negative charge, more the negative charge, more was the deflection. Second, the deflection depended upon mass of the particles. Mass of the particles. It was seen that lighter the particles, more was the deflection. And thirdly, it also depends upon the strength of the magnetic and electric fields. Strength of the magnetic and electric fields. So, more the voltage applied through the electric field, more was the deflection. Okay, so you just look at the figure once again. What did we say in this? That we are taking two electrodes, two metal discs. One is the cathode and the other one, that is the anode. Okay, and when this beam of light is subjected to the electric field only, the deflection is towards A. If it is only the magnetic field is applied, the deflection is towards B, and if both are balanced, there is going to be no deflection. Okay, now by calculating, keeping all these things in mind, he calculated the charge to mass ratio and charge to mass ratio of an electron. That was calculated to be 1.758 into 10 raised to power 11 coulombs per kg. Okay, by carefully observing the electric and the magnetic field, the EM ratio that was calculated, where M that is equal to mass of the electron in kg and E that is equal to charge on the electrons. Clear? So once the EM ratio was calculated, it became very important for us to separately calculate the charge and mass of the electron. So charge of the electron was discovered by an experiment which was known as Millikan's oil drop method. Millikan oil drop method. Right? So this was found by Millikan's oil drop method. Now what is Millikan, what did he do? Now again you look at the figure. The figure consists of a box, okay, and that cuboidal box that is divided into 3 different compartments by putting 2 metal plates in the center, right? Now what did he do was he took some oil droplets and he sprayed the oil droplets in the first compartment. He dropped the first, you can say he with the help of a sprayer he sprinkled certain oil droplets in the first compartment, okay? Then there are 2 plates. Both the plates over here, they are charged. The upper plate has a positive charge and the lower plate has a negative charge. 1 drop was allowed to fall from the upper compartment in between the charged plates. Okay, 1 drop it was allowed to fall from the upper compartment in between the charged plates, and this oil droplet that was observed with the help of a telescope. Now what was done here was that in the central compartment, in the compartment where both the plates are present, there was, he subjected X-rays or irradiated that particular compartment with X-rays. These X-rays, when they were travelling, there was certain gas which was present inside the compartment, and these X-rays, when they were travelling with speed, they knocked out certain molecules from the gas, and these molecules had electrons, so the electrons were also knocked out, and the oil droplet which was present, it captured that electron. Okay, we know that the electron is negatively charged. It was already suggested by the cathode-ray experiment that the electron is negatively charged. So this droplet also becomes negatively charged now, isn't it? So when this droplet is negatively charged, there are 2 forces which are applying or which are acting on this particular droplet. One is the gravitational pull of the earth, which will attract it towards the lower plate, and the other one is the positive terminal of the electric field, which is going to pull it upwards. Now by balancing both the gravitational force is not easy to balance. So what we do is that we balance the charge with respect to the gravitational force. Okay, so when we balance the electric field in such a manner that one oil droplet which we are observing, that is suspended to the center. Right? Now when it is suspended to the center, it is not moving at all. It is now stationary. When it is stationary, at that particular point, the charge on the plate was measured. And that charge was taken to be the charge on the electron. Okay? And by observing this, the charge on the electron that was calculated to be 1.6022 into 10 raised to power minus 19 coulombs. Have you understood the experiment? So let's see it once again. Millikan, what did he do? He took a cuboidal shaped box, right, in which he put 2 metal plates. These 2 metal plates were charged, and he sprayed certain oil droplets in the first compartment. One of the oil droplets was subjected to the middle compartment, which had the charged plates on the upper and the lower side, and this oil droplet was observed. At the same time, X-rays, they were irradiated in the middle compartment, and these X-rays knocked out certain electrons from the molecules of the gas. These electrons were captured by the oil droplet. Okay, now we have the oil droplet which is charged. There are two forces which are acting on it. One is the gravitational force and the other one, that is the force which is applied due to the electric field. By balancing both the forces, or by balancing the electrical charge in such a manner that the oil droplet that is suspended in the center. Okay, and then the charge that was calculated, and the charge was observed to be 1.6022 into 10 raised to power minus 19 coulombs. Henceforth, we could also now calculate the mass of the electron, and the mass of the electron was given by charge upon charge to mass ratio. Okay, the charge on the electron was 1.6022 into 10 raised to power minus 19 coulombs, right? And the charge to mass ratio, that was 1.75 into 10 raised to power, how much was it? 11 coulombs per kg. Now we know that charge on the electron is negative. Unit negative charge, this is known as, and the charge to mass ratio would also be negative, right? When this was calculated, the charge was the mass was calculated as 9.11 into 10 raised to power minus 31 kgs. Right? Now this mass, this is known as the rest mass of an electron. 9.11 into 10 raised to power minus 31 kg. This is known as the rest mass of the electron. Sometimes this term is used in the questions. Okay, so you have to remember that the rest mass of the electron, rest mass means when the electron is not moving. Then the mass is given as 9.11 into 10 raised to power minus 31 kg. But in case the you can say the electron is moving, then mass of moving electron, that is given as rest mass of the electron upon 1 minus under root of V upon C square. Or you can also take it as you can also write it as this. It is equal to rest mass of the electron upon 1 minus V upon C whole square, right? Where V, that is equal to velocity of electron and C is equal to velocity of light, right? Now if in case the electron is moving with the speed of light, that is velocity of electron becomes equal to C, then in that case the mass of the electron, that is the mass of the moving electron, that is going to become equal to infinity, right? If we are saying that the electron is moving with the speed of light, if V is equal to C, then in that case the mass of the electron, that becomes equal to infinity. And if velocity is greater than C, right? If velocity of the electron is even larger than the value of the velocity of light, then we cannot calculate the mass. Therefore, mass of the electron, that becomes imaginary or hypothetical. Right? this, we know that hydrogen has only one electron. Yeah, so we can also compare the mass of electron with that of hydrogen, because hydrogen was taken as standard in the previous years. For many years, hydrogen was taken as a standard this thing for many calculations, because that was the simplest kind of atom which had only one electron. Right? So let's compare the mass of hydrogen with the mass of electron. Mass of electron relative to that of hydrogen atom. Mass of electron relative to mass of hydrogen. Now when we are talking of mass of hydrogen, we know that the mass of hydrogen atom, that is equal to 1.008 atomic mass unit. This we have done in the last chapter. So if we convert this into grams, we multiply it by 1.66 into 10 raised to power minus 24. So to convert it into grams, it will become equal to 1.008 into 1.66 into 10 raised to power 24 grams. Right? Now if we are comparing both, we can take a ratio. That is mass of hydrogen upon mass of electron. Mass of hydrogen, when calculated, when we calculate this, it comes to approximately 1.67 into 10 raised to power minus 24. And mass of electron, that is 9.11 into 10 raised to power minus 31 kg. Okay, so when we calculate this, or we take this in grams, because we are taking this in grams, so let's take this also in grams. So in grams it is going to be minus 28. Right? So when we calculate this, this comes to 1837. It means that mass of electron, that will be equal to what? Mass of electron will be 1 upon 1837 the mass of hydrogen atom. Okay, so mass of electron, as you can see over here, it is very, very less as compared to that of hydrogen. Now we can define electron. So what is an electron? It is a subatomic particle, as we had discussed initially. It is a subatomic particle having a unit negative charge. Having a charge of minus 1.6 into 10 raised to power minus 19 coulombs. 1.602 into 10 raised to power minus 19 coulombs, and having mass 1 upon 1837 times of the mass of an atom of hydrogen. Okay, so it's a subatomic particle having a unit negative charge and having a mass of 1 upon 837 times the mass of hydrogen atom. Okay, now once electrons, they were discovered, the nature of electrons, that was also seen, and it was seen that electrons, they were the major constituents of all matter or of all atom. Okay, why they were the major constituents? It was seen that whatever the source of electron was, every electron had a mass of 9.11 into 10 raised to power minus 31 kg, and it had charge of 1.67 into 10 raised to power minus 19 coulombs. Okay, depending upon this, it was suggested that all atoms constituted of same kind of particles, subatomic particles, which were electrons. Right? So electrons, the maybe whatever, it will have the same charge, it will have the same mass, it will have the same charge to mass ratio. Okay, so electrons from all sources, they are going to be similar. Then later on it was seen that when we are talking of matter, matter is not charged all the time. It is electrically neutral. Otherwise, if matter was charged all the time, we will feel current with whatever particle we are touching. Whatever article we are touching, we are going to feel current in that. But that does not happen. So it means that matter, that is electrically neutral. Now to, you can say, give reasons as to why the matter is electrically neutral, it was suggested that there should be certain positively charged particles present in the matter or present in the atom. These positively charged particles were discovered by Goldstein and they were known as protons. Right? So let's go on to the discovery of protons. Alright, so discovery of anode rays. The discovery of anode rays was done by a scientist whose name was Goldstein. What did Goldstein observe? He took the same kind of apparatus as was taken for the cathode ray experiment. But in this case, instead of taking a normal cathode, he took a perforated cathode. Perforated cathode means a cathode which has holes or canals. Okay, and the anode was normal. Right? So this is the negative terminal. So this is known as the cathode and this is known as the anode. Okay. When a gas was taken inside this, again we are doing the same kind of experiment. So when a gas is taken inside this, the same was observed. That is, the cathode rays were traveling from the cathode to the anode. Behind this, he kept a zinc sulfide screen. Behind the cathode, he took a zinc sulfide screen and he observed that there were certain rays which were being emitted from the anode and they passed through this perforated cathode and hit the zinc sulfide screen. And these rays, because they were originating from the anode, they were said to be anode rays, and as they were passing through the holes of the cathode or canals of the cathode, so they were also known as the canal rays. Right? Now, when the characteristic of these were, you can say the canal rays was taken, when the characteristics was observed, they had all similar characteristics which were observed for the cathode rays. That is, they travel in straight line, they casted a shadow, they had heating properties, they produced X-rays, then they had mechanical properties, everything was same. The only two differences which were seen were, number one, they were deflected towards negative terminal of the electric field. Okay, so what is happening over here? They are being deflected towards the negative they were positively charged. Clear? Then number 2. They had an opposite direction in the magnetic field also. Like when we are talking of the cathode rays when placed in the magnetic field, they are deflected towards the south pole. Right? So anode rays, they are deflected towards the north pole when they are placed in the magnetic field. Rest all the characteristics was same. Right? The EM ratio was also calculated, and the EM ratio of the anodes that depended upon the gas. The EM ratio depended upon the gas, which suggested that the anode rays were different for different gases. Okay, and the stream of particles which were present in the anode rays, they were known as protons. When the charge was taken, when the charge was measured, the charge of the anode rays, or the charge on this, that was 1 unit positive charge, which had the same value as that of electron, 1.602 into 10 raised to power minus 19 coulombs. Clear? Chalo, for today we'll do only till